The Smart Plant Care System, an IoT-based project designed to monitor plant condition and automatically support plant care. The system monitors three main environmental parameters: soil moisture, temperature, and humidity. Sensor data is collected by Raspberry Pi node and then distributed to different microservices for storage, analysis, control, alert generation, and user interaction. The project follows a microservice architecture where the components communicate mainly through the MQTT and REST web services. The diagram shows the overall architecture of the smart plant care system. On the left, we have the Raspberry Pi sensor node that they collect soil moisture, temperature, and humidity measurement and publish them through MQTT to the message broker. The broker distributes these MQTT message to the interested services. The ThingSpeak Adapter receives sensor information and communicates with ThingSpeak through its REST API. The analytics service processes the sensor information and uses historical data to perform more advanced analysis. It contains the soil moisture, temperature, and humidity control logic and can generate command for the system. We also add an LLM service. Analytics act as a REST client and communicate with Olama, which provide the REST API and run the Gemma 3 model, and the LLM is an additional interpretation layer on top of our existing analytical result. The report and alert generator process the system condition and generate alert when is necessary. The Telegram bot provide direct interaction with the user, while the Node-RED provide the graphical dashboard. Finally, the catalog is the central registry of the architecture. Different resources and microservices register themselves in the catalog and using the REST web service, and other component can query it to discover the information they need. MQTT is mainly used for asynchronous sensor data, command, and alert, while the REST web services are used for service registration, service-to-service request, cloud communication, and the communication between the analytic and the LLM service.
Mosquito serves as the central MQTT message broker for the system. Its primary job is to act as asynchronous publisher-subscriber messaging hub, decoupling edge sensors from analytics module alerts generators and cloud adapters. When a sensor publishes a message, Mosquito immediately distributes it to all subscribed microservices without requiring direct client-to-client connections. Let's look at Mosquito.conf, which control how the broker behaves. Line 1 tells Mosquito to enable persistence state storage. Instead of storing subscription and QoS messages strictly in RAM, it saves state metadata to disk. Line 2 defines the exact container directly where Mosquito writes its state file MosquitoDB. Line 3 directs broker lag to a standard output. Line 6 disable mandatory username and password authentication during development, allowing our local microservices to connect seamlessly without hard-coded secrets. Line 8 binds the broker to listen on the network port 8083, the international TCP port for unencrypted MQTT communication. As you can see, in the left terminal, Mosquito subscriber is actively listening on topics. Our Raspberry Pi nodes are publishing live sensors every few seconds. You can see real-time updates for temperature, soil, moisture, humidity, and UTC timestamps streaming directly through Mosquito. In the right terminal, we execute Mosquito Publisher to target the topics directly with a consume JSON payloads. Because Mosquito handles asynchronous publisher-subscriber routing instantaneously, any message published on port 8083 immediately fans out to all subscribed consumers.
In our smart plant care system architecture, the Raspberry Pi Edge service acts as the main node for collecting sensor data and controlling plant devices. This service lives inside directory and runs as a separate microservice. It sends the sensor data to broker, receive control commands, and work independently from the central cloud server. This Docker file contains the container environment for the Raspberry Pi sensor application. It starts from Python 3.11 Slim image, which is a lightweight version for Python that helps keep the container small and efficient. The working directory is a set to /app, which is where the application file will be stored inside the container. Next, it defines an environment variable to configure the application. The Python variable improves how the application runs by preventing unnecessary bytecode file and make sure logs are displayed immediately. The device variable stores information about the sensor node, such as its ID, name, and type. The MQTT variable configured to communicate with the MQTT broker, including broker address, port, and topic, for sending sensor data and receive the comment. The Docker file also set the connection to the catalog service and define timing settings such as how often the device publishes the data and how often it registers itself. After the configuration is complete, it copied the requirement file and installed all the requirement Python libraries. Then it copied the JSON file, the main, and the simulator. Finally, the cmd command run main.py automatically when the container starts. The requirements.txt file contains the Python libraries needs for the sensor application to work. It includes request, which is used to make a HTTP request, for example, when the device registers itself with a catalog service, and also include PoMQTT, which allowed the device to communicate through MQTT by sending sensors data and receive comments from the MQTT broker. This JSON file configs the Raspberry Pi sensor application. First, it sets the device ID, the catalog services URL, and a 10-second interval for publishing data. Next, the MQTT info section configures the connection to the MQTT broker. This includes the client ID, port, and a specific topic used for sending sensor readings and receiving comments. Finally, the simulation block defines the starting value and fluence rate to generate the fake temperature, humidity, and soil moisture data. This file is responsible for simulating the physical environment of the plant sensor node. The main component in this file is a plant simulator class, which generates realistic sensor value and handle control comments. At the beginning, the file imports several libraries. JSON is used for formatting the control state output. Mass is used for the environmental calculations. Random adds a small variation to make the sensor reading realistic. Threading handles safe access to shared data. Time, data time, and time zone provide the precise time tracking, and time provides type annotation for the code. The function noUTC ISO create a UTC timestamp is ISO format without of microsecond. This timestamp is added to the sensor data and controller logs so each reading and action has a clear time reference. Inside the plant simulator class, the constructor init initializes the simulator. It stores the device ID and accepts an optional simulator configuration dictionary to set parameters like base value, amplitude, decay rate, and initialize soil moisture. It also created threading.log to prevent a data conflict between the sensor update and incoming comments. The simulator initialized a set variable for soil moisture, temperature bias, and humidity bias, while tracking the timestamp of the last update. The control state dictionary stores a current actuator state for watering temperature control and humidity control, alongside information about the latest comment, its execution time, reason, and sensor type. The fraction function calculates the current time as a fraction of 24-hour day. This allows the simulator to create a natural daily pattern, such as high temperature during the day and low temperature at night. The updated environment state function responsible for changing the simulator environment over time based on elapsed seconds. Soil moisture naturally decays over time to represent water consumption. However, active control command dynamically modify the environment, allowing soil moisture to increase or decrease temperature bias to cool or heat, and humidity bias to adjust before clamping value within a realistic limit. The read temperature, read soil moisture, and read humidity function generate individual sensor reading. They combine daily sine wave pattern, active control biases, and random noise to simulate real hardware reading. Each value is limited to a realistic range and rounded to one decimal place. The collect data function is used to gather the latest sensor information. Before collecting data, it updates the environment state and returns payload formatted according to Sentinel standards with base name, base time, and measurement units, while retaining flat attributes like device ID, temperature, soil moisture, humidity, and timestamp for backward compatibility. The handle comment function processes commands received from the MQTT broker. It parses the comment payload, updates the internal control state with detail like reason and sensor type, and sets active state for watering, cooling, heating, or humidity adjustment. It also prints action message and update the simulator control state. The print control state function displays the current simulator control state in a JSON format, including active control state, the latest, command received, command time, reason, and a sensor type. Overall, this file acts as a virtual plant sensor node. It replaces real hardware sensor by generating realistic data, adhering to SNML standards, responding to MQTT control commands, and providing sensor reading that can be published to the rest of the smart plant system. File is the main program of the Raspberry Pi sensor node, responsible for connecting the device to the catalog service, communicate through MQTT, collect simulated sensor data, and publish the data to the rest of the system. File import the requirement libraries. JSON is used to encode and decode message as well as reading configuration file. OS is used to read environment variable, treating all the different tasks to run concurrently in separate threads, and a time is used for delay and timing operation. The requirement libraries handle HTTP communication with the catalog services, while Pow.mqtt manage MQTT communication. Finally, the plant simulator class is imported from the simulator module to generate simulated sensor readings. The main component is the sensor node class. This class represents the Raspberry Pi devices in a smart plant system and encapsulates all the registration, message, and simulator functionalities. Inside the init function, the sensor node receives a basic information such as device ID, catalog URL, broker address, port number, topic base, publish interval, and simulation configurations. Environment variables are checked first to allow dynamic runtime, configuration overrides, and provide arguments are used as defaults. The function cleans the catalog URL and dynamically creates the full sensor and common topic use the device ID. It then initializes the plant simulator with a given simulation configuration and set up the MQTT client with a unique client ID and callback function for connection, disconnection, and incoming message. The register device function handles registration with a catalog service. Constructs a JSON payload contains the device ID, name, type, sensor topic, command topic, and status. It then sends an HTTP POST request to the catalog device endpoint. The function accepts status codes 200, 201, or 409 as successful registration, allowing the node to process seamlessly if it already registered in a catalog and return false if the connection error occurs. The registration task function runs the registration process in a loop. If registration fails, it waits for 5 seconds and tries again until the device successfully registered with a catalog service. The next section contains the MQTT callback function that handles network events. The onMQTT connect function is called when the node connects to the MQTT broker. If the connection is successful, it sets the connection flag and subscribes the command topic with a quality of service level 2 to ensure reliability. The onMQTT disconnect function updates the connection state flag when the MQTT broker connection is lost. The onMQTT message function handles incoming MQTT command message. It decodes the JSON payload from UTF bytes, like the received comment, and pass the payload containing the comment type, reason, and a sensor type to the plant simulator handle comment function. This allows the simulator to adjust the watering, heating, cooling, or humidity control. The MQTT loop function maintains the MQTT network connection. It continuously attempts to connect to the broker with keep alive timer and start loop forever to process network traffic. If an error occurs or connection is lost, it waits 5 seconds before reconnecting. The publish loop function responsible for periodically send sensor data. When the MQTT client is connected, it collects SNML sensor readings from the simulator, convert it to the payload into the JSON format, and publish it to the sensor topic using QoS level 2 with wait for publish function to ensure reliability delivery. It then sleeps for a configured publishing interval before the next update. The run function starts the sensor node. It logs a startup message and launches three separate background threads for catalog registration, MQTT loop processing, and sensor data publishing. The main thread then enters the loop to keep the process runtime while listening for the keyboards interrupted to shut down cleanly. The stop function safely shut down the sensor node. It sets the run flag to false and gracefully disconnects the MQTT client. Finally, inside the main section, the program loads configuration setting from config.js, including the catalog URL, device ID, publish interval, MQTT broker information, and simulator setting. It instantiates sensor objects with three parameters and starts the device by calling the run function. Overall, this file acts as the main controller for the Raspberry Pi sensor node. It connects the plant simulator with a catalog service and MQTT broker, receives comments, generates animal sensor readings, and reliably publishes data to the smartplant system.
Catalog is the central registry of our smart plant care system. Its main responsibility is to keep the shared information that other microservices need. All microservices communicate with the catalog through the REST API. For example, the devices can register themselves here, and Analytic can request configuration value from the catalog. In this folder, we have the data folder, as you can see, that contain the catalog.json. Also, we have the config.json, Docker file, the main part, and the requirement. Here, the requirement just contain the external Python libraries that required by this service, that we just need the cherry pie. Now I will explain the catalog.json. Here we store the dynamic information of the catalog service. In our project, we divide it into three sections: the users, devices, and the services. Each user has a unique ID, Telegram ID, the name, device, role, and status, and the important part is the devices that show, for example, it belongs to which user. The second section for us is the devices, that here we register the all Raspberry Pi sensor node. Each device, for example, has a unique ID, the name, command topic, status created, and the last topic. For example, the command topic is the topic where the device received the command from the analytics service, and we also store the device status together with created at and the last update. Created at here also show the date and the time that it first registered, and the last update is refreshed when the same device register again. The third section for us here show the services. This work as the service registry of our project. Here we store the microservices, for example, the alert generator, the Telegram bot, the analytic, and all of them. Each service has their own ID, name, type, endpoint, status, created at, and the last update, as we can see, and similar the meaning of created at and the last update. So overall, this is the catalog JSON, is the dynamic registry of our system. Then we go back to describe the config.json. Here, unlike the catalog that contains the dynamic information about the user, device, and service, here we have the configuration file, the configuration value of our system. The first parameter, we had the catalog file. This defines the path of our catalog data. In the Docker container, the catalog data also stored. And the main Python file reads this path from the configuration instead of the hard coding. The next section is the server. That the host port and the log screen just here specify and identify. As you know, the log screen is set to true, which enable the cherry pie log on the console. And the next section is MQTT. Here we define the broker and the port. And the next one, the thresholds we specify for temperature, soil moisture, humidity, each of them the minimum and the maximum. Now that we have seen where the catalog data and configuration are stored, the next I will show you the Docker file and explain this one. In the Docker, the purpose of this file is to define that how we build and run the catalog as an independent Docker container. At first, we use the Slim version base image that is provide a Python 3 because we use it because it's keep the container lightweight. Next, we have a workdir app that we define it as the working dictionary inside the container. The following command and executed relative to this directory. After we define the 3 environment variable that prevents the Python from creating unnecessary code, and the next one make the Python output directly to the console without the buffering. And the config file tell the application where to find the catalog configuration in the config.json that we mentioned. After that, we copy the requirement into the container and install it. We have just the cherry pie into in the requirement. And the copy main and config.json. Main contain the catalog application logic, and also config contain the configuration that I explained before. We expose 8000 that indicate the catalog service use this port, which is the port that used by the cherry pie. And finally, the cmd instruction to run the main Python. So when this container starts, Python execute the main catalog application and load the configuration and prepare the catalog data file and start the cherry pie REST service for us. Now I explain the main part of the catalog. Here at first we have some imports that we need for the services. Then before our class I define a load config definition. It means this function load the configuration of catalog service from the config.json that we have here. And here I first check the config file environment variable, and then in with open I open the file in read mode and use the json.load also. After that we have ensure catalog file that is responsible for make sure that the catalog.json exists before our service started. And we have if os pass exists, it means I check whether the file already exists or not. If the file exists, that the function run. But if the file doesn't exist, we have this necessary that create a dictionary here, make there for us, and we have the user, device, and services define this minimum structure. And then with JSON dump, here we write this structure to the catalog.json. For example, if the file exists, preserve it, but if not, initialize a valid empty catalog. Then again, we are going to describe our class, the catalog web service. After the initialization that we have, we define this class expose true for the true that allow for cherry pie to use the services, and later also I have the method dispatcher, so the HTTP can handle this, for example the get, post, push, and the delete, all of the methods. At first we have init. The catalog file is a dynamic persistent catalog that contains the user, devices, and the services. So config file is a separate configuration file. Here with self-config that I store both paths as instance variable because different methods need to access them. The self lock here creates an R lock. This is important because CherryPy can handle the multiple requests, and more than one request could try to modify the catalog.json. Then we use this lock around read, modify, or write, such as the post, put, delete for all of them. Then in the file management, we have a load catalog. That's a load catalog read the dynamic catalog JSON. It opens the path that we store it and use the JSON load to convert it to the JSON into the dictionary. Here we have the except, if we have except is the error. The two important things, error, that's OS error represent a problem accessing or reading the file, and the another one, the code error, that means the file exists but it's not a JSON. I mean the JSON is not valid. After that we have a save catalog that here it received the Python dictionary and write it back to the JSON file. And so most modification operations follow this pattern. Then we have a load service config. This function is different from the previous one, and read the dynamic registry data for us, but the previous one. But the load service config here read the config.json. This we have this separation, because this separation mean the user, device, or services can change dynamically without mix the configuration. Also here we have this one, the error, that file access error and invalid JSON return the none, and the REST layer can then return the correct server error for us. In the helper method, after the management, I have some small helper function, we call it, that avoid repeat the same logic as a get or post or put. Here in the current time self, generate the timestamp that used when device and service register or update. Also we have the date time now time zone UTC, that explicitly we use the UTC, so all container and service have a common time reference. Then for error response here, we have the status message that centralize the REST error format. Then with the CherryPy, this line change the HTTP status code, and here I return a JSON error message. Then in find by ID is reusable search function. That item can be the user list, the device, or the service list. For example, item ID is our ID that we want to find this as a keyword. Then for here we can also say that iterate over the collection and compare the ID. If it's we find it, I return it, but if nothing, I return the none. In the find position also is similar to previous, but instead of return the object, it returns the position of our list. Then for the position item in enumerate, give us the both the index and the item, both of them. We go to the check catalog, is important helper because almost every REST operation need a valid catalog. So we have a load catalog here, try to load our data, and if it's not or if it's failed, we have a HTTP error 500. And then finally we return the catalog now. Here in the validation section, before that storing information, we validate it. Validate the user. For each user, I require the ID, telegram, name, and devices, and the function loop through this required field. For example, if not instances, verify the device is a list, because one user can be associated with multiple device ID. As you know, if everything is valid, the function return us none. And the validate device, for a device, the required field also had ID, name, type, MQTT topic, and command topic. Also, we point that if it's not, I check not only the field exists or not, also it has a meaningful value for us, convert to a string, and using the strip rejects empty string and strings containing only spaces. At the end of this, we also validate the service. It has the same pattern for the device, and register by ID. That is really important part. In registration part, this is also important for registration of the device and our microservice. Here in the position, self find position by ID, we check that this ID exists or not, then generate the current timestamp. Then if the ID doesn't exist, this is a new registration for us. Then we explain that the new item set default here give us the active status if none was provided, and set the creation time, set the last update time, all of them, and then append this new item to the list, and return both the action and the resulting. Then if our ID exists, I don't create the duplicate one, okay? I just copy the object and merge the new information for to the list. Also, after we had the updated item ID that existing time, the ID doesn't change here, and the original creation timestamp we keep it, but there is just one thing that modified, and this is the last update. After that, we go to the get, the important part of the REST API. The first HTTP method for us is get, as you know, and this part is important because we rely on the structure that we learn, the URI and the params. URI is used because to understand which REST resource is requested, and param, as you know, used for optional query parameters, for example, the telegram ID. At first, we set here to 0 if there are no URI component. The client requests the root endpoint, and we return a welcome message, the available endpoint, the summary that we have a user, devices, and all things. Then we have the URI 0 again here. Otherwise, the first URI element identify the resource, that it can be the user, device, service, or our config. The get users, here, as we have for users, the API support the 3 operations: the complete user collection, one user by user ID, and one user use the telegram ID query parameters. For example, if the len is more than the 2, if the pass has too many components, I reject it with this error. And we use the param variable here, that if the query contains telegram ID, I convert it to the integer part, except this type error, that if the value cannot convert it, the input so is invalid, and we return this 400 error. After that, we describe the get devices. Here, the device section use the same REST structure also. There is no matching user, we have the error 404. Then if the len is equal to 2, I mean there are 2 URI components instead. The second one is treated as the normal user ID, and we use the find by ID that return the user if it exists, or 404 if it doesn't exist. So finally, without the ID or the Telegram query, get return the complete user list and its count. Actually, we have the same logic as we said for the get devices. For devices, we return the all device, and if we specify the device ID, we use it the ID to find just the information of that one. And as an unknown device, we return error 404. The next one, the get services. For service ID, return just one registered services we have, and then we go back to the config. That is important because here the config endpoint is different for us. Configuration is not stored inside the catalog.json. When another, for example, microservice request config, the catalog called the load service config, and read the separate config.json. So if the service config is none, if the configuration file cannot be read, we return the HTTP 500 error. Otherwise, we return the configuration as a JSON. Here I want to emphasize that this endpoint is for analytic, because the analytic can have the centralized settings such as threshold from the catalog that we can see later. Then we go to the post that is used to create a user and to register a device and the services. You know that we have a CherryPy tools JSON in and out. That is for the JSON request body, and this is for the response. Then we have the if len URI equal to 1. It's not equal to 1. That post work on a collection endpoint, so I expect exactly just one URI component. If it's not, we have error. Then CherryPy place the parsed request body in CherryPy request.json, and if not, the body must represent just one JSON object, otherwise we have a error 400. Then we have a description of self-lock. Before we modifying the data, we have the lock. That inside this, I load the current catalog, modify it, and save it. And this protect the complete the read, modify, write, and all operation, rather than the protecting just, for example, the write. Here we have a post users that we first called the validate user. That invalid data, invalid user, we raise error. Then also duplicate the self find by ID. And unlike device and service registration, duplicate user are not refreshed here. If the same user ID, for example, exists, I return the error again. So for a new user, role defaults to user and status defaults to active. Again, we have post devices as we have here. Again, we start with validated device and then call register also by ID. Then in action that device is equal to self-registration ID. Here we have the return action tell us that whether the device was created or the updated. Then we save it, and again 201 if it's created. And I mean 201 is always return this content that is created, and if it exists that refreshed or update, it's just 200, that is okay. Again, for the post services, here it's exactly the same mechanism, the same procedure. There is just one difference, that we have a validate service and the service collection that allow the other microservice to register themselves in the catalog without creating the duplicate service. And also in the post, if post is attempt on an unsupported resource, we return a error that 405 method, for example, is not allowed. We go to the put, that is responsible for updating existing the user, the service, or the devices. We mentioned it's not equal to 2, unlike the post. A put is require 2 URI component, the resource and also the resource ID. If the ID is missed, for example, we have the another error 400. And the updated file cherry-pie request .json, that the JSON body contains only the field that the client wants to update. Here for resource and item ID, we separate the URI into the resource type and the target ID. Because the put modify the data, the same lock is used again. In the put user, for a user update, I first locate its position in the list, and if it doesn't, we have a error 404. And then for the user's position, we copy the object and merge the requested field. Then that is mean the request body cannot change the identity of our resource. And after they validate the complete result. Again, here we have the put devices and device ID. That's finding the existing object, we copy it and merge the new field and validate the result and also save it. For example, in one section that we have the last update. For devices, I also refresh the last update because the device information may be changed. Again, here in the put services, service update uses the same logic as we say in the devices, and it preserves the service ID, validate the object, and update the timestamp, and save it. If put is used for an unsupported resource, again we have a error. Then for the delete section, this is the last REST operation. Here we need just JSON out. Actually, there is no JSON in because the resource to delete is identified by the URL, and I don't require a JSON request body. So if it's not to we have to must contain the resource and its ID. If we have a missing ID, we have the error. And the lock also again is used because deleting also modify the persistent catalog. And in the delete user, for user, I find the position using find position by ID. But here we return, if not find, if it doesn't exist, we return 404. Otherwise, I use pop to remove it from the list. Then in delete the devices, it's the same structure, but device deletion has one additional step because the user can contain references to device, and this is the step that for user in catalog users. After we remove the device from the registry, we iterate through all the users, and if the deleted device ID appears in a user's device list, we remove the reference as well, and this keeps the relationship between the user and device to be consistent, and for example prevent the user from referencing a device that is not exist. We go to the delete services. Service deletion use also the same logic and find the service by position, return 404 if it doesn't exist, and remove it using the pop, save the catalog, and return the delete service. Then also stop it with 405 error. The main part in the bottom, if the name equal to main, the main execution, the final part is for initialize and start our catalog service. As we know here, first we resolve the external configuration file path, and again Docker can provide this through the config file environment variable. Then config, load config here, it means the load the configuration into Python dictionary, and the catalog file, the location of the catalog itself comes from the config.json, and ensuring that it exists before starting the REST server, make sure that the catalog exists. Then in the cherry pie configuration, here, as we learned before, the key part just is the method dispatcher that map HTTP method to the corresponding method in our class. So all of the method that post, put, delete, all of them works. This is what gives the class its the REST structure, I mean. Also here we cherry pie server settings are also read from the config.json. Cherry pie also read the config.json, the host, port, the log screen, and then we create instance of catalog web service and the mount of the cherry pie that mount the object and apply the method dispatcher. And at the end we have a start and block that start the cherry pie server and stop it or waiting for the new request. That was the whole concept of the main catalog. Analytics service is responsible for processing the sensor data that coming from our Raspberry Pi devices. The Raspberry Pi published the temperature, soil moisture, and humidity measurement through the MQTT, and the analytic subscribe to this sensor topic and receive the measurement in real time. After the receiving data, analytic compare the sensor value with the threshold that are centrally stored in the catalog. And based on this comparison, it determines the state of each sensor. For example, if the value is low, the normal, or high. According to this state, it can generate the appropriate control command and publish the analysis result through the MQTT. Also, our analytic work with the historical sensor data. It can request the previous measurements from the ThingSpeak and perform the statistical analysis. For example, checking the trend and detecting the unusual value. Our project also works with LLM. We have an optional LLM component that's using Ollama and the Gemma model. The important point for our project is that the LLM is not responsible for the main control decision. The threshold comparison and the statistical calculation performed by our analytic Python logic. The LLM just received the calculated historical statistical result and give a short human-readable interpretation of trend, the anomaly, or monitoring the recommendations. So the control logic remain in our code, while the LLM is an additional interpretation layer. I mean, if the LLM is unavailable, the basic analytic and our control functionality can still work. The structure of analytic here, as we can see, config.json, the Docker file, main, and the requirement that here contain the Python dependencies for this service is cherry pie, request, and Paho MQTT. Now we are going to describe the config.json. Here, as we can see, divide into several sections that has different responsibility. At first, we have the service that specify with ID, name, type, the host and port. This is the configuration of analytic service. We dedicated the host and the port. Registration, retry delay means if the analytic cannot register with the catalog immediately, it wait for 5 seconds. Then we have the catalog. Here is the configuration. is what we can see in the Docker, and the threshold refresh interval defined as how frequently analytic refresh the threshold configuration from the catalog. In the ThingSpeak Adapter, also here we can see the adapter is available in this port, and the history endpoint specify the REST endpoint, also the history result, and the analysis interval. Interval means define the interval used for the historical analysis process, and the history result define how many historical results should be requested. In this case, we just determine the 30. For the MQTT, we specify the broker, the port, the sensor topic. As we know, this wildcard is the MQTT multi-level. It means the analytics subscribe to all sensor topic for the all sensors that we have from each Raspberry Pi. And at last, the quality of service is one, provide at least once delivery for us. In the analytics section, we specify the minimum history point, define the minimum amount of historical data that we require. The z-scoring define the level used by the statistical logic for identify the unusual value, and the trend epsilon used when evaluating the trend. For example, it provides a small tolerance for deciding whether a trend should be increasing, decreasing, or is stable. Here we specify the commands that for each sensor we define low, high, or normal. For soil moistures or humidity, we keep this command name configuration. Then we consider LLM as I define. The enable true, so the LLM integration is enabled. The provider here is Ollama, which allow us to run the model as another service, and Ollama service is available on this port, and the selected model is Gemma. The timeout here define how long analytic can wait for LLM response, and at the end the instruction that the model should interpret only the historical statistical results that we have in analytic. The main thing that I want to mention in the LLM is Python perform the actual sensor comparison and statistical calculation. And just the LLM explain already the calculated results in human readable language. That was our config. Also, we have the Docker file, as I described before, and the requirement. Our complete logic is on the main part. For the analytics service, we have many responsibility here that register in catalog, receive the real-time sensor data, compare the value with threshold, generate a command, and retrieve the data from the ThingSpeak and perform the statistical analysis. And also at the end we have the LLM. Okay, we see all of them. We skip the import parts and go to the class. Here we mention the sensor fields and map the sensor name to the ThingSpeak field, because in the ThingSpeak we have the field 1, field 2, field 3, but the historical data returned by ThingSpeak, and this map tell us the code which field, for example, belong to which sensor. And in the sensor rule, define the command key mapping. For each command we have a low, high, normal, and we know the key that point to the actual command string is stored in the config.json, and the code can generate a state, for example the low or low command, read the corresponding configuration key from the sensor rule, and finally obtain the real command from the command section. In the init section, we have the receive the already loaded configuration dictionary. Is the same as we mentioned in the main part of the catalog. The configuration is the same. We separate it into the small dictionary instead of repeatedly, for example, config.mqtt. We store it into self.mqtt config. And also the same for the LLM. instead of a direct indexing. I mean, if the LLM section is missing, the service get an empty dictionary instead of immediately raise the error. All of them in a RLOC we used because the service has MQTT and the REST request, and all of the thread different part of our program may access the same data at the same time, so we create a RLOC to be the safe. And these are the main in memory data structure. For example, the latest data store the most recent MQTT sensor payload for each device. The command history store the recently published command, analysis history, last command and last historical analysis, store the historical analysis was last start for each device. Then we have a threshold information that we keep it separately. At the beginning is known because we receive it from the catalog, and updated at, and also threshold ready the event. And event is a simple thread. When threshold are successfully wrote, we call it set. And self MQTT connect false. This boolean track the MQTT connection state. And here we create a PAHO MQTT client. The client ID, as you know, come from the configuration. And the clean session mean that the broker doesn't keep the old MQTT session. Here we have the callback assignment. PAHO automatically call this method when a connection established or disconnect, or when a message arrives. Finally, we validate it before the service continue. We validate the configuration and go to the valid config. Validate the local analytic configuration here. The sensor topic, command topic, define the MQTT topic key require our application. And the for key is required topic for if the key, for example, is missing or has an empty value, we raise an error. For rule in self sensor rule, it's instead of the manually list everything, every command, I read the required key directly from the sensor rule. Here we have a now UTC ISO that we just mentioned, get the current UTC time, remove the microsecond and convert it to the ISO format. The sensor topic return the configuration MQTT, and the command topic here for us build the final command topic by combine the configuration topic with the device ID. Analysis topic also use the same pattern for the historical analysis. The catalog registration. We register to the catalog as we had for every microservices. Build the JSON object sent to the catalog when analytic register itself. And the endpoint is a build from the Docker service ID and configured REST port. We are going to the register service. In the register, perform the actual the REST configuration. The post JSON argument automatically serialize the Python dictionary into JSON request. The timeout is 5, prevent analytic from waiting, for example, forever if the catalog cannot respond. And both 200 and 200 var are accepted. As we know, 201 represents a newly created, and 200 represents a updated or refresh. And also the error, that they accept that the error that we handle related problems such as the connection error. The registration startup task is a startup loop. The while loop continue only while registration is unsuccessful, and when registration succeed, we have a registered service return true. The condition becomes false, and the thread the end. Between failed attempt, the thread is sleep, for example, here for the configured retry delay, so it doesn't continuously send the request and stop it. The extract threshold. Here, receive the configuration response from the catalog and extract the threshold, and then this allow to response format. If the response contain a config key, for example, we have a that dictionary is used. Okay, otherwise the response itself is treated as the configuration. And the threshold, say that I retrieve the threshold object and verify that it's a dictionary. Then we validate it, and I create a new normalized dictionary instead of directly trusting the JSON file. For sensor type, iterate over the same supported sensor used by the rule engine, and the minimum, maximum that are explicitly convert to the float. If the minimum is higher than maximum, okay, we can raise the error, it's invalid. And the method return a clean threshold dictionary by sensor name. We go to the load threshold from the catalog. Actually request the centralized threshold. We call the catalog config endpoint, raise for status, convert the HTTP error status code into exception, that to handle the error. And the new threshold, the JSON response is passed through the validation method before being stored. And because thresholds are shared with the MQTT rule engine, I update them under the lock and compare the new value with the old value. This allows logging only when there is an actual change. And the self threshold ready set say that after a successful load, the event is set to indicate that real-time threshold evaluation can safely run. In the threshold refresh task, there is a permanent background loop for threshold synchronization. We say that while true, unlike the registration startup task, this loop run continuously. Loaded self-load. If loading succeeds, the service waits for the normal threshold refresh interval. But if it fails, it waits for the shorter retry delay. The refresh interval if is a Python condition expression that it chooses the sleep duration based on the Boolean result. The get threshold snapshot. Here, this method safely return a copy of the current threshold that we have. They return the copy. We use it because the threshold structure contains nested dictionaries. And MQTT connect. Here, this callback automatically execute, as we know, after the Pahu connect to the Mosquito. In Pahu, return code 0 means successful connection, as we know, and the client subscribe to the sensor topic and quality of service. After the connection, analytics subscribe to the configured topic, and the quality of service is also load from the configuration. If connection, for example, failed, MQTT stay false and the return code is locked. And on MQTT disconnect, this is also the MQTT connection state as false and log the return code. For the on-MQTT message, this is important because every real-time sensor message enter analytic through this callback. The sensor data JSON load, we know MQTT payload arrive as a byte and decode it, convert the byte to the task. JSON load convert the JSON text into a Python dictionary. Then we have a device ID, extract the device ID. Without a device ID, analytic cannot associate the message with a device, so the process stops. And the MQTT topic add to metadata field. MQTT topic and receive add, for example, store the time, analytic receive the payload. For the with self log, the latest reading is stored using the device ID as a dictionary key, and the two separate calls, self evaluate control and the self maybe run historical analysis, that after store the reading, these two pass triggered and evaluate control, perform immediate real-time threshold, and maybe historical analysis decide whether it is time to run the more expensive historical statistical analysis. The threshold control remain fast while the historical REST access and LLM process are handled independently. The MQTT loop here maintains the MQTT network connection, and it continuously attempts while to keep this connection alive. Loop forever is a PAHU network event loop, we know, and receive the MQTT and trigger the callback. Publish JSON. Here, this is a general MQTT publishing helper that used by different part of the analytic. If not, the method first check the local connection state and convert a Python dictionary into a JSON text for MQTT. The return info, PAHU publish call return and information object, and compare its return code with the MQTT error success and return a boolean. Here the interesting point is there is a no wait for publish here. There is important because publish can happen from the MQTT callback path, and blocking the network callback thread can prevent the further MQTT processing. In the publish command here, this method publish the actuator command that's selected by the rule engine. We have a last command, self.last command by device means get safely reads the previous command for the current device and the sensor, and if the last command equal to the command return, this is the duplicate command suppression, and if the required command has not changed, the method returns immediately. The self.command history here means its history is limited to just the latest 200 command. This prevents then the in-memory list from growing forever. And the self-last command by device set default ensure a dictionary exists for the device before store the last command. Then in the evaluate sensor, the function contains the actual threshold classification for just one sensor. At first we have a missing sensor value or ignore, and we normalize it, the value to a float, and then threshold comparison we have if lower than the minimum or greater than maximum, the deterministic control logic. Then we classify low, high, or centralize the threshold. And then the command key, this is line select the correct command key name. The F string we have combine the current state with the command and the sensor rule to map that to the appropriate entry in the configuration. And the self.command key here, the real actuator command is then take from the config.json and pass to the publish command. Evaluate control in this method evaluate the complete incoming sensor payload. The threshold here take a snapshot of the current catalog threshold, and if the threshold are not ready yet, no control decision is made. For instead of repeating the same threshold logic, I loop over every supported sensor and we reuse the evaluate sensor. We go to the historical data analytic. In the get history, request historical data through the ThingSpeak Adapter. The endpoint come from the configuration, and the param argument create HTTP query parameter. We send device ID and the requested number of historical result. Here HTTP error raised automatically, and on success I return the feeds list. If the key is missing, also return an empty list. We extract the history value. This method extracts clean numeric value from the ThingSpeak and read the selected ThingSpeak field. Then missing or empty measurement are skipped using continue. Value are converted to the float and append to a clean list. Also invalid numeric value are also skipped here. In the mean section, mean calculate the average using Python sum divided by the number of the value. We have the standard deviation, calculate the population standard deviation. With fewer than, for example, 2 value, the code returns 0. And then the generator expression calculate the square distance of each value from the mean, and the average of a square distance is the variance. Another statistical is linear trend slope. This method estimates the trend using a simple last square linear regression in the size equal to the len, the number of historic measurements stored in the size, and then because the x-axis is just the sample index, the mean x position can be calculated directly, and the y-mean is the average sensor value. The numerator and denominator, both of them calculate, for example, the numerator calculate the covariance and the denominator calculate the variance. Then the ratio for us is the slope. In the trend label, this function converts the numeric slope into a readable label. We have the epsilon is a tolerance configured externally, and I don't want a tiny numerical slope to automatically become an increasing or decreasing trend. Then we have a historical sensor analysis. This method combines all the statistic calculation for one sensor. For example, the minimum point require number of measurement come from the configuration, and if there is not enough data, the function doesn't pretend to perform meaningful statistic. It explicitly returns the insufficient history. And this calculation here for enough data calculate the mean, standard deviation, trend slope, and the latest measurement. For the z-score, express how far the latest value is from the historical mean in unit of standard deviation. And the result contain the history size, the latest value, mean, standard deviation, minimum, maximum, and all of things that you can see here. In the anomaly, ABS consider both unusually high and unusually low deviation. Also, the threshold come from configuration rather than being the hard code. In the run historical analysis, this method coordinates historical analysis for one complete device. In the feeds, retrieve the historical feed, and for sensor type, iterate over the mapping between the meaningful sensor name and the ThingSpeak field name. Then for each sensor, I extract the numerical value and call the historical sensor analysis. Then in the LLM integration, we have a Python LLM that only after deterministic statistic are complete we call this LLM. This is very important, and the LLM doesn't calculate the mean or z-score or everything. Python calculate all of them. Then LLM just ask to interpret the already calculated statistical result. The self-history append here means the complete result, including the optional LLM interpretation, stored in the memory, and the list is limited to just 500 record. Then in the self-historic analysis, we save the current timestamp, so the interval logic know when this device the last time analyzed. In the self-published JSON, the historical analysis payload is published to the device analysis MQTT topic. And then if fetching history fail, we have the error. In maybe run historic analysis, decide whether historical analysis should run after a new MQTT when the new MQTT arrive, and the last time means if the device never analyzed, at the default we set it to the 0, and if time less than the interval, it means the current time minus the previous analysis time give us the elapsed interval. If it's too soon, the function return immediately, and if not, then the threading, if analysis is due, I start a separate daemon thread. This is design choice because the run historical analysis make REST request to ThingSpeak and may also call the LLM. So running them directly inside the MQTT callback would block the sensor message processing. And in the self-log, for self-last historical analysis, I reserve the timestamp immediately after starting this thread. In the interpretation with the LLM, this method handles the operation of LLM interpretation of historical statistic. If not, the LLM can be disabled completely through the configuration. If disabled, analytics simply return an object saying interpretation is not enabled. In the LLM input, intentionally create a reduced input object, and the LLM receives the device ID, analysis type, history, and the sensor. It doesn't receive control authority or raw instruction. Then we have this prompt. The prompt is constructed from fixed instruction in configuration that followed by the calculated analytic JSON. And then we try response request post that the LLM is accessed through Olama's REST API. Then this means the request specify the configured model, send the prompt, and set the stream to false. So the service receive one complete JSON response rather than to just have, for example, the sequence, stream sequence. And the timeout also come from the configuration because the local model generation may take longer than a normal REST call for us. In the interpretation result, the model output is retrieved from the response feed, and the strip remove the leading and the white space. In the LLM error handling, we say that the LLM layer is designed to fail safety, but network error, invalid response data, and JSON error are caught. And instead of following the whole historical analysis, the results contain interpretation, the none together with an error message. And in the REST API here, analytic also expose a REST, and we have a JSON out, tell CherryPy to serialize the return Python structure as a JSON. We have a pass, the query, that query receive query string parameter. In the root endpoint, if not pass, an empty pass represent the root endpoint. We have a health, device command analysis. The health, in this version, the status field itself is always returned as OK, while readiness detail are separately exposed through MQTT connect or threshold loaded. In the device endpoint, return the latest MQTT sensor data that is stored in the memory. In the command and analysis, also we describe it here for each of them. Also in the analysis endpoint, return the historical statistical analysis. And these are the same as we said before. Also for the rule here, expose the current threshold snapshot and the configured command mapping. At the end, we have if the pass doesn't match any supported resource, CherryPy return us the error. In the life cycle, the start and stop. For the start, the background process need by analytic, this thread that we have, the registration, threshold, and MQTT. Registration handle initial catalog, registration, and retry it. In the stop, also, we have performed a simple cleanup by disconnecting the MQTT client. And this is the also main execution block. Is the application bootstrap that the configuration path come from the environment with app config JSON is the default, and the JSON configuration is load before the service created. Then create the service, run the constructor, and validate the configuration. The calling star launch the 3 background thread for us. And at the end, this is the request dispatch, the service mount, and method dispatcher tell CherryPy to dispatch the HTTP request according to the methods that we have in the class, the get, put, post, and CherryPy session are also enabled. In the configuration, the server host and port come from the analytics service section that we have a config.json, and the log screen is enabled so CherryPy log appear in the console. And in the shutdown subscription, disconnect the CherryPy stop event or our stop cleanup method, and start and block. As we know, start the CherryPy HTTP server, and block keep the main Python process alive, which also keep the Docker container running, and then block it.
The alert generator is a microservice in the smart plant care system responsible for monitoring plant health, generate a real-time warning when the environment condition breach safe limits, produce a historical reports, and provide device state data to the web application. At the beginning, like the other microservice in the system, it used the same standard Python 3.11 Slim-based image and set the working directory inside the container to the app. It also set a Python environment variable to prevent a bytecode generate and ensure real-time log output in a container's log. Docker file define key environment variable which default value for service registration, server port 8091, catalog service URL, MQTT broker connection, and a ThingSpeak Adapter URL. These can be overridden dynamically when running the containers. Then it copies requirement.txt into the container and installs requirement Python dependencies, which out of catching extra files. After installing dependencies, it copied the main and a config into the working directory. Finally, it exposed port 8091 for incoming HTTP REST traffic and it specifies the command python main.py to start the microservice when the container launches. Overall, this file ensures the alert generator can be easily built, configured, and deployed as a containerized service within a smart plant system architecture. This file contains the JSON configuration setting for alert generator microservice. It defines the service identity, host, and a port 8091 for the REST API, alongside the URLs for communicating with a centralized catalog service and a ThingSpeak Adapter service. It also specifies the default number of historical records for a report generator and include the MQTT info block, which configure the MQTT broker settings and topic patterns used for subscribing the sensor telemetry, monitoring threshold, analytics event, and publishing warning alerts. In requirement.txt, we have CherryPy for running a HTTP REST API server, requests for making HTTP calls to the catalog service and a ThingSpeak adapter, and PoMQTT for handling MQTT connection, subscribe to the topic, and push alerts. This file is responsible for running the alert generator microservice. The main component in this file is alert generator service class, which processes live telemetry, generates real-time alerts for threshold violations, produce historical report, and service REST API endpoints. At the beginning, the file imports several libraries. JSON is used to format and parse JSON payloads. OS handle pass utilities, threading allow multi-threads, state management, time manage, delay, and data time and time zone provide the UTC timestamps. CherryPy run the REST web server, how.mqtt client manages MQTT communication and request communicate with external HTTP services. The helper function in nowUTC ISO create a UTC timestamp in an ISO format with out of microseconds. This timestamp is added to the alert payloads and health state outputs, so each event has a clear time reference. Inside the alert generator service class, the constructor init initializes the service parameters, including service ID, name, host, port, catalog URL, ThingSpeak adapter URL, default history, result limit, and MQTT broker details. It creates a threading lock to protect shared data, initialize an in-memory telemetry dictionary and alert list, and sets up the MQTT client with the callback handlers. The average helper function calculates the mean of a list of numerical value and rounds it to the 2 decimal place. Return a 0 if the list is empty. Register service function handles registration with a central catalog service by sending an HTTP post request containing service details to the catalog endpoints. The registration task function runs this registration process in a loop, retrying every few seconds until the service is successfully registered. The MQTT callback functions manage broker connections. The MQTT connect function set a connection status and subscribe to both raw sensor telemetry topic and the threshold analysis topic with a quality of service 2. The MQTT disconnect function update the connection status when disconnected, and on MQTT message decodes incoming JSON message and routes them based on a topic prefix. The process sensor message function processes raw telemetry data from the sensor nodes. It tags the payload with a topic and a timestamp metadata, then update the latest telemetry data for the device in a thread-safe state dictionary. The process analysis message function processes threshold evaluation message from analytics service. When a message indicates a low or high threshold violation, it constructs an alert payload containing the device ID, alert type, current value, threshold type, and a timestamp. Then calls publish alert. The publish alert function publishes a warning alert to the MQTT broker under a smartplant alert device ID using a quality of service 1. After successfully publishing, it stores the alert in an in-memory buffer that keep up to the 200 most recent alerts. The fetch catalog devices function retrieves registry physical devices from the catalog service via HTTP. The merge devices function combines catalog device records with a live telemetry data from memory, providing a complete view of action and registered devices. The generate report function creates performance summaries for a device. It queries to the ThingSpeak Adapter service over HTTP for a historical data feed, extract temperature, soil moisture, and humidity reading, compute average value using the average function, and return a structured health report. The get method implements ThingSpeak REST endpoint using method dispatcher in handle for service overview, for health status, for merged device telemetry, for recent alert, and for generate historical performance reports. The start and stop function handle service lifecycle by spawning background threading for a catalog registration and the MQTT connection loop, while ensure clean MQTT disconnection when the service is shut down. Finally, inside the main section, the program loads a setting from catalog.json, instantiation alert generator service, start background task, configure CherryPy to serve on a host and a port using method dispatcher, and start the web server. Overall, this file acts as a main controller of the alert generator microservice. It connects MQTT messaging with the HTTP REST services, processes telemetry and thresholds events, generates real-time alert, and provides a device monitoring and reporting capabilities.
ThingSpeak Adapter. This microservice acts as an edge-to-cloud telemetry bridge. It subscribes to MQTT sensor streams from Mosquito normalized payload formats, dynamically manage cloud credentials, and sync historical data directly to ThingSpeak Cloud Channel via REST APIs. Starting with requirements.txt. Specify the external Python libraries required for this microservice. CherryPy provides an embedded multi-threaded HTTP web server for REST endpoint and health monitoring. Requests handle outbound synchronous HTTP calls to our central catalog and the external ThingSpeak API. Paho MQTT connects our adapter to the Mosquito broker for asynchronous messaging. Moving to config.json. The configuration is structured into distinct operational sections. Service and catalog define the service identity, sets the endpoint to port 8080, and points to the catalog service URL with the built-in request timeouts and retry delays. MQTT connects to the broker host on port 8083 and subscribes the wildcard topic smartplant sensor using quality of service level 2 for reliable delivery. ThingSpeak specifies the base API URL reference, the ThingSpeak user API key, environment variable for secure authentication, applies a channel naming prefix, and caps historical feed queries to 100 entries. Field mapping and storage maps local metrics such as temperature, soil moisture, and humidity directly to field 1, field 2, and field 3. It also sets the persistence paths for our registry file. Next, in the Docker file, we built from a lightweight Python 3.11 Slim image and configure non-buffered output for real-time terminal logging. We set environment variable default for networking, service paths, and file location. The build install our dependency, copies the source code, creates the persistence data directory, exposes port 8080, and launches main.py at runtime. Here in channel registry, we see the persistence mapping generated during runtime. Each sensor node, RASP1 through RASP4, is linked to its assigned ThingSpeak channel ID. Alongside, it's decided to write and read API keys. This guaranteed that device credentials remain intact across container restart. Now, let's take a deep dive into the core engine of our service, main.py. This file is structured into 7 distinct architectural layers, from thread safe state handling and zero-touch cloud provisioning to SNML, payload normalization, asynchronous MQTT ingestion, and embedded REST API. We begin at the top with app config. Our static utility, helper class. First, now UTC ISO generates a standardized timestamp without microsecond for accurate timestamping across microservice. Next, load JSON, file handle files, loading and initialize, ensuring that missing directory structure or configuration file are automatically created on both with default value. And finally, save JSON atomic implements atomic file persistence instead of overwriting file directly. It writes updates and temporally.temp file first, then use os.replace to swap it in. This guarantees that power outage or container crash mind write will never corrupt our channel registry on disk. Moving down, we have shared state. Because our microservice run background thread for MQTT event handling, catalog registration, and HTTP REST queries concurrently, thread safety is critical. Shared state wrap all shared memory access inside a reentrant lock, threading.rlog. The methods set latest message and get latest message manage our incoming telemetry buffer, while set last upload status and get last upload status keep track of our cloud upload results. For registry management, get registry return a safety copy of active device mappings, get device channel, look up individual nodes, metadata, and save device channel updates the mapping in memory before triggering an atomic disk write. Let's examine ThingSpeak Adapter service. The primary class of orchestrating our pipeline. In the constructor init, loads config.json, initialize share state, construct our PAHO MQTT client using a configured client ID, and bind our connection and message callbacks. Below initialization, helper method like service config, catalog config, MQTT config, and ThingSpeak config cleanly extract specific configuration blocks. Notice the user API key method, instead of hard-coding sensitive credentials, it looks up the environment variable name defined in our configuration and retrieve the key dynamically from the system environment, throwing a runtime error if it's missing. To integrate with our microservice mesh, the adapter dynamically registers with the central catalog built registration payload, structures the metadata containing our service ID type and endpoint register service, then issue an HTTP post request to the catalog service URL. To make this resilient against startup order dependency, registration startup task runs inside background thread on boot, repeatedly attempting registration every few seconds until the catalog confirms success. When telemetry arrives from a new unmapped sensor node, ensure channel for device called create channel for device. This issue an HTTP post request to ThingSpeak to generate a new cloud channel, configure mapped field label, extract the return, write and read API keys and save them straight to channel registry.json. Below that, normalize sensor payload, standardize incoming data. It natively parses SNML, sensor markup language formats, extracting device IDs from base name fields, converting base timestamp into UTC ISO strings, and iterating over measurement arrays. Crucially, it includes a fallback loop for standard flat JSON objects, ensuring full backward compatibility for any sensor format. Now let's look at real-time message processing. When connected to Mosquito, unconnect subscribes to a smartplant sensor with quality of service level 2. MQTT loop keeps this loop running on a dedicated thread with an automatic retry loop for network reconnection. When a message arrives on message, dedicate the JSON normalize the payload, stamps arrival metadata, update share state, and passes the data to the process sensor data. Process sensor data resolves the channel credential using ensure channel for device, format the payload via build update payload, and sends an HTTP post request to ThingSpeak update endpoint, logging the result and updating our upload health status. Finally, the bottom of main.py define an embedded HTTP REST server powered by CherryPy, root API, returning a directory of available endpoints, health API, returning health status, UTC timestamp, recent telemetry, and last upload result for monitoring tools. Latest API, serving the most recent raw sensor reading. Registry API. For security, it explicitly sanitizes the output, stripping out private write and read API key before returning public channel mappings. History API. Expose history, acting as local proxy that fetch historical cloud feeds directly from ThingSpeak while enforcing max result limits. At the execution entry point, the main block instantaneous ThingSpeak Adapter service print operational parameter to the console, launches our MQTT and Catalogue background threads, configure CherryPy, dispatches, and socket ports, and starts the HTTP servers on port 8080. This completes the full code structure of main.py. Now I publish a test SNML payload to Mosquito. In the left terminal, adapter receives the MQTT message and confirms. Simultaneously, on the right, the live ThingSpeak dashboard charts for temperature, soil moisture, and humidity plot our new data point in real time. To demonstrate execution, I open Health in the browser. As you can see, the REST endpoint returns a status OK, timestamp, and the latest upload metadata. Under the API key tabs, we find the credentials that secure our cloud channel. Used exclusively by our microservices to authenticate HTTP post requests when publishing telemetry. Read API keys allow internal applications such as our Raspberry Pi history endpoint or Node-RED dashboard to retrieve historical feeds securely without exposing administrative access.
Telegram bot is an automated program that runs inside a Telegram message app. It can respond to standard applications and then interact with users or other systems of the network. Bots are commonly used for alerts, customer support, data reporting, and integrating external service into Telegram chats. Now I'd like to explain the Telegram bot part. The Typical network has the Telegram database of several backend servers. And read configuration communications with Catalogue service interact with MQTT for alerts and commands, and retrieve data from alert generator service. At the top of the file, we import all of the necessary models, and then we create a class which is called Telegram Plan Bot. This class contains all the methods needed to initialize the bot, manage communication, handle user commands, process alerts, and publish commands to the bot. First is init. The job to initialize everything the bot needs, and know the runtime configuration, read the configuration file, and get and modify the Telegram bot tool. And then it creates the MQTT client and the message broker and register all the handlers. And the bot will create a method called the load JSON. The method read a JSON file from this and return as a Python dictionary. And the next method is load runtime config and also the NSG. These two files that read the corresponding things from the configuration. Let's show what is in the configuration. The config has three parts. This is for message and this is for the runtime. Look at this runtime that will have everything, the initialization, some URL, and the message. We have everything that in the Telegram bot message will show later. Another very important method is safe get JSON. The difference in that it gets the JSON from HTTP GET request to give the URL, wait for the response, and change the JSON into Python dictionary. Now let's move to user management. One of the most important method is get alert generator UI. This method is used for service discovery. Instead of depending only on the hard code URL in the topic, type after the catalog service for available service. It looks for a service with titled alert generator and then usable service endpoint. We found this, then we get endpoint. This is the URL. If found, I will use the fallback, which is a hardcode one. So let me check on the catalog. And we can find the service, which is called alert generator. This is what I mentioned before. Now, the method get catalog user. When the user in the catalog matching the Telegram ID, it's allowed for that Telegram account with the registered system users. I also find the user in the catalog. The method get authorized user should all active user and return their Telegram IDs. These users are the ones who are allowed to receive alert and enter the support. One of the things that focus on the data which is active. If it is inactive, it's not allowed to use this platform. Yes, we'll show you them. Next, get user devices. Return the devices that a particular user is authorized to access. Each user will allow to manage 2 devices. Different users manage different devices. The method is authorized user ID. Check for Telegram users valid. Alright. Is twice allowed for user. Check whether a given device can be accessed by a system user. And if the user status changes, now the status is active. So we can use the Telegram bot as usual. And if I change the state into inactive, something will change. You are not authorized, which means that if the user's status is not active, you cannot use the Telegram bot. Now we turn into the service registration. Method registers service and a host message payload about information to register the Telegram bot and service. I will do that. The registration loop, it will be run in the background, continuing when the service starts, and check about the service. Okay, this is the Telegram bot service. Then after that, method to get device map, and we can get a device list from the catalog and change the dictionary. And get allowed device map. We can get the allowed device by different IDs. This different user will be assigned by different devices. Get a device data. query the alert generator service to get a real-time status of the device. The command topic method is the MQTT topic used to send commands. This part is about MQTT, and this is MQTT loop. It will be another thread that run on the background to keep the MQTT service. Okay. Method publish command used to send a control message device over MQTT. Title and the topic. The format alert message define the alert message format with this, and it will be used for the form alert message, send alert message. The alert action keyboard. If there is a reached alert, and there will be can be used for operation. If the temperature alert will start cooling, meaning the humidity is notify the user for alert method, send an alert to authorize the users and text the relevant part. If your former device status is the format of alert, this is the format report. This is a menu keyboard and will show all the functions. The button that will be used. Click, device alert, need to report commands and device, and will be returned about the message in this format. Device keyboard for user create a list of buttons for each device the user wants to access. The command action keyboard, the control button to send a command to device. Yes, control buttons. Message register handler attach Telegram handlers for chat message and callback queries. Message require authorization message, check whether users authorized for handling normal message. Message require authorization callback perform the same check for button click. The important part is the on-chat message and receiving context message and rows them according to the command. Yeah, command, different command will correspond to different handle method. Start, help, the device, status, alert, report. And if there's no message like this, it will be unknown. Finally, the method on callback query handle button press for Telegram is the place where the bot responds to main action, such as returning to the main menu, opening the device list, an alert, and so on. Send a command to the device. And then the run method that run the two thread and the background is the regional connectivity tool. And this is the main function. Create a Telegram bot, send, and run. Let me show how to operate on the Telegram bot. This is a Telegram bot and start and show welcome to smartplant cases involved. Choose the action below. There are four things. As you can see, here is the device. I have a content control and this is other no alert available. These are the reports. These are the reports for 2. This is for 1. And then press that. And then command run and do some operation about the device and particular device needs. And also I can help, and there are some instructions. Now I change my account, change to another account. Look, there's another account, and I do same thing again and prepare the device. They are different from the previous account. That's 3 and 4. Yeah, no alert available. And I can take the report. Then we go back. Now let's wait for the alert happen and what. Now there's a alert happen. And see the alert message. High, low soil moisture. The value is lower than 0. So what we want to do is to increase the work rate. Okay, let's go back. Let's go back and see the alert. Look, there's alert record. There's alert happen. Note that is a wisdom program to design or write together component devices. To study and online single flow based uses flows on the browser space approach to create automatically workflow without writing. In our project, we use for dashboard for remote monitoring and control. Let's focus on the notepad folder. What is inside the notepad folder? There is the data folder and the Docker file. The Docker file used to build the notepad container image. The package JSON and ProJSON are set to be auto start. Then we focus on data. The NPM can have the cache and log. We use to speed up the dependency installation. And the link, we use the library for them. The node modules that store external node nodes. They are all auto-generated when the Docker starts. Free config file about the node, the runtime, and the users. And then the flow is our core function. Main flow file store, deploy the node and connections. The flow grid.json can store the encrypted credentials using the flow, such as identity, password. The package JSON that lists the node dependence from the npm install. The dependencies will be used. And the setting.js is the manual red file. Let's see about this flow.json. At first, the inject and every 5 minutes. Every 5 minutes, use get to request on this URL the catalog service to request the alert generate service. We can see about this. If we find the alert generator, then we store the endpoint and we send the endpoint by using the get. The URL is the one we found before, and we request for the alert generator service to find the threshold. The threshold will be stored and will be used later. Now, let's see the next part. Next part is every 5 seconds. We use the get from the ThingSpeak Adapter to get the data, and this to collect and distribute our data to the three gauge node. Freeze this threshold and we will show the gauge the temperature, the soil moisture, and they are 4 similar processes which corresponding to 4 devices. And also this one use this threshold to drop alert, and if the alert happens, it will send alert to this node. This node will collect the alert and send to the template, and the template will use this code to change the CSS, to change the layout of the browser, and to change the default blue to red. That is, there are all different kind of red. Red means alert. And then the next process is still similar as before, but we request every minute. You request from the ThingSpeak Adapter and collect and distribute data, and then we use the chart to use a line chart to show the historical data. Because of this, we update the line chart every minute. Why we use this for 1 minute and we use this for the 5 seconds for the to use get to request for the ThingSpeak Adapter, because we don't want to be conflict. The conflict will be wrong so that it will be slow for this part. Yes. The goal is more important for the real-time data update. This is not for as important as before. We need to be sure that this one can update the data in the real time. Then let's focus on the dashboard. There are 4 devices on the sidebar. We can choose one of them and then you can see the left. There is a real-time method, count, and the temperature, the thermometer, and humidity. Let's see the color. The yellow shows that the temperature is a bit low. Thermometer and humidity, they are green, which means that they are in the right zone. And the right side, the historical chart, it shows the temperature, the moisture, humidity, the historical, because the node on the plot And every 20 minutes, there's a point, and we update the plot every minute. Look, change is color changing to red, which means that there is something in alert. So which one is alert? So the story motion in the recipe is lower than the threshold. So we can do some operation. We can use the Telegram bot to do this.
Docker Compose. In this section, we are examining the central Docker Compose, orchestration configuration for our smartplant care system. This file manages our entire microservice architecture, bringing up 11 interconnected containers across core infrastructure, edge to cloud bridge, analytics, AI LLM processing, notification channel, dashboard, and simulated Raspberry Pi edge node. Let's walk through how services are configured, wired together over the internal Docker network, and boot in sequence. We begin with our foundational infrastructure layer, Catalogue. Serves as our central service registry, running on port 8000. It mounts local persistent JSON storage to app data and maintain active system configuration. Mosquito. Act as our central MQTT message broker using the Eclipse Mosquito 2 official image exposing port 8083. It handles all asynchronous publish-subscribe traffic between our edge sensor nodes and processing service. Both services are configured with restart unless stop to guarantee high availability. ThingSpeak Adapter. It connects local MQTT telemetry to external MathWork cloud channel. It loads sensitive credential directly from our root.inv file and exposes port 8080 for health probes and historical data queries. Notice the depend on directive is strictly waits for both Catalogue and Mosquito to start before booting. Moving into intelligence and data analytics. Ollama pulls the official Ollama latest image, exposing port 11434 for local LLM interface. It mounts a name Docker value Ollama data to persist AI model weight across container rebuild. Analytics runs our core data evaluation engine on port 8090. Coordinates with the Catalogue MQTT broker, ThingSpeak Adapter, and Ollama to evaluate plant health metrics in real time. For processing and user interaction, alert generator built using a dedicated Docker file context on port 8091. It monitors sensor conditions against threshold and generate event alert over MQTT on a smartplant alert. Telegram bot serve as the user interface for mobile interaction injected with Telegram bot token from our .inv file. If subscribes to alert topics, forward real-time warning to users, allow remote control commands, to be published back to the edge actuator. For system monitoring and control, Node-RED exposes a web dashboard on port 1880. On a startup, its inline startup commands automatically installed Node-RED dashboard inside data before launching the runtime server, giving operators an intuitive graphical control panel. Finally, at the edge layer, we define 4 simulated sensor nodes, Raspberry 1 to Raspberry 4. Each node uses a shared Dockerfile context located under Raspberry Pi Dockerfile. Every node is assigned a unique device ID and device name via environment variable. They automatically register with the catalog, read simulated hardware sensor, and publish telemetry packets every 10 seconds. All 4 nodes depend on Catalog and Mosquito being fully operational before they begin publish.
Now that we've walked through the theoretical architecture and detailed each microservice, let's see the smartplant care system in action. Now let's launch the entire system with a single command. Docker Compose spins up all our isolated microservices. As you can see from Docker Compose PS, all 9 containerized services are up and healthy. The Catalogue Microservice acts as our central registry. Here on port 8000, we can see all registered devices, services, users, and configurations. Mosquito runs a lightweight MQTT broker on port 1883, handle all pops of message routing between sensor nodes and the backend services. Every 10 seconds, our sensor nodes publish live temperature, humidity, and soil moisture telemetry to the Mosquito MQTT broker. Analytics is our data processing engine. As you can see on port 1890 and a Docker log, it continuously calculates moving average and evaluates the sensor stream against plant threshold.
Straight how the LLM part of our project works. On this port, we run it. As you can see, Olama is running, and if you want to see the API and the tags, here it shows that our configuration use the geometry, and for see the LLM we use the analysis port. It works on this port, analysis. As you can see here, rely on this history. We have the interpretation. Here is a summary of the IoT and the suggestion and recommendation. Also each of them dedicated with the timestamp. So that was the most important thing in our project, and it shows completely the LLM integration for us, and how analytic combine this historical statistic with the LLM generated human readable interpretation.
Alert Generator creates alert and reports. On the endpoint 1891 alerts, you can see the recently alert events, and on the report, it generated plant health report with the average readings. Node-RED is a visual dashboard at the port 1880, show the live information and the graphs and the control toggles. Telegram bot is our mobile app interface. It sends an instant push alert, handle a comment, and lets users trigger manual comments, and also we have access for reports for each devices. And ThingSpeak Adapter push all telemetry to the cloud for a long-term storage and visualization. And that's how our complete system runs live. Thanks for watching.